right?
For this, yeah.
And then
Audio.
before introducing our convener this morning, I have a couple of three announcement. In case you don't know me, my name is Wayne Lee. I'm the faculty of civil engineering, and then I was fortunate to establish a Rhode Island Transition Center in 1992, which was our centennial year, and then I'm serving as a director. And actually that year we started this forum, and then we appreciate your coming. You are really a loyal member of this forum. First announcement is do not look at that clock. That we are still working on, okay? It requires high-tech, repairment, so we are still repairing. Hopefully, when we have new building, I think we may have a better clock, but so that's what I'm trying to tell you. Second announcement is we do have the wastewater treatment plant for biological grade, but we don't have the first floor. We have a second floor, so when you go this staircase, you need to get out. There is the wastewater treatment plant. Okay. If you have any difficulty to walk here, we also have the best elevator. Can you believe we have an elevator, two-story building? So if you take an elevator, you also can meet the wastewater treatment plant. Also, second floor, we have some posters prepared by students. So if you are boarding with this forum, you can go on the second floor and then you can look at those some posters. All right. One of the reasons we are late this morning is we have a little technical difficulty with the sound system, but we have two best technical staff from Engineering Computer Center, and they
I'm Jack Reed, and I want.
Look at this one. What a wonderful, So we are almost ready to start.
Thank you.
Right? Thank you very much.
No problem.
Okay. See, what a timing, So now it's time. Oh, actually, and also the lunch will be 11:50 at University Club, across the street. So do not miss lunch. When you come here, you have right to have the best lunch in the state of Rhode Island. Okay? With this, I would like to introduce this morning convener, Professor Param Nashashari. He is currently president of URI Faculty Senate. With this, please give him our big hand.
Thank you, Wayne. I want to welcome you to University of Rhode Island on behalf of all of the faculty at the university. I don't know if this group knows much about what the Faculty Senate does, but we're not just the legal entity, but we conduct the business of the university. The Faculty Senate has some 26 committees that pretty much run the business of the university, anywhere from academic program scheduling to specific courses that we teach to how we teach them. So as I like to remind our university president many times, the faculty is the university, because without them there would be no university and we wouldn't be able to do our work. But I'm here this morning to help with the introductions of the speakers this morning. And our very first speaker, who is my dear friend and colleague, Dean Ray Wright, the 7th Dean of the College of Engineering, will be our first speaker. He has a lot on his mind these days, and I'm sure he will share that with you. Right?
Bahram did not mention that he was the 16th, so I learned everything from him, and anytime I have a problem, I always go to him, and we meet at a very exclusive place to discuss things over beer. So I've actually been here for quite some time. I've been here for 33 years. I'm on my 34th year. And it's very unusual, for a member of the faculty for so long to be dean. But it just happened that we got into a situation where I ended up being interim when Bahram made the choice to step down. And it was a time that I was able to compete for the job and get the job. And I've been dean now for 7 years, and this is actually the 8th year. And I think it's amazing because I'm a civil engineer too. Wayne and I have worked together over the years. I actually hired him, so I didn't hire you, but I interviewed you. And when I was just a young assistant professor, Wayne had come from Saudi Arabia. That's where he was located. And Wayne came over to here, and we had a breakfast, and he and I were sitting and talking at a breakfast, and I can remember turning to him and I said, "Oh, you're from South Korea. Do you know?" Now, isn't that crazy? I knew one guy from South Korea, and I was going to ask Wayne if he knew who this person was, because I had gone to graduate school with him in my master's and PhD, and I became pretty close with him. And Wayne turned and he said, "He was the best man at my wedding." I said, no, you must have misunderstood who I was talking about. And it turned out that the one guy that I knew from South Korea had been the best man at his wedding, and he had come from Saudi Arabia. And so it was a connection that we made very early on. But it's amazing that we have 27 years, of the Transportation Forum, that has been going on. So I congratulate you for the longevity of the forum and everything. I think it's fantastic. Bahram mentioned that I have something on my mind these days, and there is. I actually, since the beginning of September, have made 57 presentations, all on the same subject. Now, even for an engineer, that's a long thing, a hard thing to do. But the presentation has obviously been important to me. I think it's very important to the college. Because if you look at the college, this particular building that we're in here was really built in the 90s, and it was a great addition to the college. But if you wander through it, what you'll see is that there are a couple of core facilities, like the Academic Computer Center for Engineering, which is located on the second floor. But there's a lot of research that goes on here. You can see across the way that there's research, that goes on, and there's a lot of research in the rest of the building. And so it added, some things to the college, but it's a relatively small building as far as square footage is concerned. So when you get a chance to see everything on the other side of this, really the most of the College of Engineering is enclosed in this engineering quad. And it was a master plan that was completed in 1956. And there used to be, all of engineering was in one building, which was the brick building, which is just outside the door to our left, which is an historic building. And in 1956, the master plan said, okay, listen, we need to build new buildings for the College of Engineering because it's growing. Post-World War II, and so we built 5 buildings. 2-story brick buildings, central corridors, no flexibility in the buildings, very little environmental controls in the buildings. But they were quick buildings that we could build in order to be able to get the people, the influx of people that were coming back from the war, back from the Korean War who were basically coming in from for engineering. And so it's been over 50 years since those buildings were built. And for the last 6 or 7 years, we have been moving towards Tuesday. And that's why it's so important to me that for the last 6 or 7 years, we've worked through the process. Now, some of you don't come from Rhode Island, so you might ask the question, well, what's this got to do with a ballot day, an election day on Tuesday? In Rhode Island, in order to get money for an academic building, you have to get it by the voters of Rhode Island. That's unlike Connecticut, where it's an appropriation. That's unlike Massachusetts, where it's an appropriation. So it's the General Assembly that makes decisions on how this money is spent. In Rhode Island, you still have to go through the governor. You still have to go through the General Assembly and get their approval. But then it goes to the voters. And if there's 100,000 people that vote and you get 50,001, you win. If you get 49,999, you lose. We have a $125 million bond on the question on Tuesday. It's the single largest bond ever in Rhode Island's history. and that says something. Well, it says something that's gone through this process of approvals all the way up to the general public. And so on Tuesday is a big day for us. What it is asking for in the $125 million is a new building that will be constructed, and the actual renditions are on these forms, which, you know, these pictures which are out in the hallway if you want to pick one up. It's looking to put all of engineering, almost all of engineering, under one building, or one roof. It's going to demolish the 5 buildings that were built in the late 50s, early 60s, and put this one building in here that's going to give us 40% more academic space and 40% more research space. It's really going to elevate us to where we need to be. You know, we're a small college because we only have 62 faculty right now. And, you know, I think one time in the early 80s we had 75 faculty, but pretty much 62, 65 faculty for maybe the last couple of decades. And our population of students was at a certain level a decade ago. It's increased 39% since then. 39% is a lot. We're at about 1,350 students right now, expecting to grow if this bond is passed. And that to me is important from a Rhode Island sense, and that's what I'm selling these days, is Rhode Island sense. We graduated 70% of our students last year were Rhode Islanders. And if you really look at Rhode Island, you know, one of the fantastic things about Rhode Island, if you're an engineer, is the number of companies that hire engineers in the state. It's pretty incredible when you start looking at the defense industry or the manufacturing industry or the service industry, the R&D industry. And we help put students, both internships and full-time employees, in these companies. And what's been great is that in order to pass through that General Assembly, we had over 30 companies that wrote letters of support for us. These are CEOs of companies. And financially, we have about $8 million contingent on the bond passing that have been given to us by companies and some private citizens. And so we're very excited about that. So this is, you know, a moment, I think, in the history of the college that is really transformational, you know, for this to happen. Transportation, of course, will benefit like all our programs within this college. And I hope that in the 28th one, when you come back, well, it won't be the 28th one, but the 29th one, when you come back, those buildings won't be there, because it's probably going to be that time sequence when this bond gets passed that we'll be demolishing and starting to build new. And I'm very excited about it, as you can see. So we have buttons, right? I don't know whether you want buttons or not. Some people say they don't want to wear buttons, but I think I stuck myself last night when I was sleeping because I wear it to bed. This is actually the key to where it is on the referendum. You know, they've put hurdle after hurdle in front of us, so this particular hurdle is that we're question number 4 on the referendum. If you're from Rhode Island, you sort of know what it is. But the first 3 above us are bonding financial questions. They're basically questions on casinos and constitutional conventions. We're the first bonded question on there, which is important. It sort of shows you where it's located, which is nice. And then this gives you the specs on the college, and you know, basically talks about, you know, where we're at as far as patents are concerned, where we're at as far as startup companies are concerned, where we're at as far as numbers of students, Rhode Islanders, graduation, and so forth. And it's nice. You can pick that up outside. So I will leave you with that. I know that's not what you expected, you know, from a dean, but you know, this is the 58th presentation, so I'm keeping count. I have until Tuesday, you know, to shut up. I got radio ads this afternoon. I have had radio ads all week. It seems like if you go to the TV set and you look at the TV set, we're on the TV set. So come Tuesday, it will be, it's a big day for this college. I mean, a huge day for this college, transformational. So if you're a Rhode Islander, don't forget to vote. Don't forget to vote for 4. Talk to your neighbors, talk to your friends, talk to your relatives, all right? Every vote counts, and you know, every vote counts for engineering. So when you see the signs, did you bring the sign? Yeah, you can see that the Q here is Engineering Rhode Island's Future. And there are lawn signs. You know, if anybody would like a lawn sign, you know, we have those. So I know it's not Q&A, but I'll ask if there are any questions, because I'd be happy to answer anything that you might have. Yes?
I've visited your website and looked at the school, engineering in particular. Have you investigated, looked into a co-op program for these students? I know you have a internships, but.
Right.
And I'm a graduate of Northeastern.
Sure.
And it was what drove me, and you talked about the local, 70% of them being Rhode Island students.
Sure.
Talking about supplying the local
Mhm.
firms with talent, and I think it's a great opportunity, great vehicle, and I was wondering if you've investigated looking into a more defined program.
I would say there wasn't a formal investigation, but I think it's been, discussed on many levels, whether that was a direction to go. We have a very good history of internships in the college, and I think that's part of probably what was on the webpage. I know the average, probably in the last 7 or 8 years, has been that about 85% of our undergraduates have had at least one engineering paid internship in their time here. And that's a very strong number, considering it's not part of the curriculum and it's not a requirement of the curriculum. And the majority of those are in Rhode Island, though a lot of them could be in New England or New Jersey or New York, or in many cases, 60% of that 80% have 2. And so now you're talking about 6 months of experience over the space of the 4 years here. And about 25% of that 85% have had 3. And the ones that typically have had 3 are the international engineering program students. And those IEP students, are working normally in internships in Rhode Island for probably the summer after their sophomore year and junior year, or their second or third year. And then usually we try to get them a job with the company that they're actually going to intern with internationally. So when they go abroad internationally, 25% of our 1,350 students are in the IEP program, so this is not a small program by any means. And we draw people from all over. I think 22 states are represented within the IEP program, and people come from as far away as Alaska and California, and obviously the Southwest. And when they intern here for hexagon metrology or for Raytheon or for Schneider Electric. And then when they go abroad to a country that they've learned the language. See, they have to learn the language. That's what makes the IEP program different. And they have to perform in that language. So when they go to Germany, and a lot of students who come in to do the program don't know the language. They're not coming in from a high school setup. They come in maybe not even having had one course in German or Chinese or French or Spanish. And they learn in 3 years enough here, and our language faculty are tremendous because they know they have to go abroad to perform. When they go abroad for that year, they get 6 months in our partner university where they're taking engineering courses in that language. They might take fluid mechanics in German. And if you can imagine how tough fluid mechanics was when you were taking it in English, can you imagine taking something like that in a language? The second 6 months, they have an internship that we arrange. So if they're mechanical engineers and they like cars, they're in BMW or Volkswagen. And so they're working right alongside German engineers. The plans are in German, the reports are in German, the language is in German. So you can imagine when they come back. So in a way, the IEP program is not a co-op program, but that is a requirement of the curriculum that they need to intern and everything. So 85% of the students, that have had internships, is pretty impressive. And we have a job fair every October just for engineers. And the Ryan Center floor is full. 50 or 60 companies come, and they come looking for internships. And the thing that is different than the rest of the university is they're paid. And so companies come, because they want these kids, to participate, because they're looking for them to be employed. Similar to what your co-op program is, it's a great way for a company to experience a student's performance and get to know that student before they actually offer them a position.
And you mentioned interviewing Professor Lee. You sat with him, you talked. It's hard as an employer to evaluate what you have in front of you. If you co-op with a company, you have 2-3 sessions with them, you get to know them a lot better, and then you say, okay, I want to invest in this individual, and when they graduate, and I'm, again, a product of that. I worked for my company for 18 years and ended up running the company.
Sure.
So it has a lot of value, and I didn't know it again.
Yeah, and I think if you look at our track record, because one of the things that I do personally as dean is I don't see every student that graduates, but I have their resumes in front of me, and so I have a clear picture of what their performances were outside the university, throughout their entire 4 years. So I track that, and I have records of the students, and I have the records of the students. A lot of the students are multiples, that they'll be with Newark for 3 straight summers. And so, you could say that's a co-op, but, they're basically moving within Newark, to different operations, and they're experiencing different things, and oftentimes it ends up in a job. So we're close, to doing that, but from a curriculum standpoint, from a requirement standpoint, is not a requirement. But the 15% that don't do it, you ask the question, what do they do if they don't do that? And to be honest with you, I'd say probably half of that 15% are lifeguards. No, and I did down in Narragansett, lifeguarding, on state beaches and that's part of, the history of Rhode Island, is that's how they grew up and everything. So I can't see us moving in that direction right now. The IEP program's 5 years, and some people have said, how can you have a 5-year program? A lot of engineering is trying to reduce it below 4. But again, we've busted the seams with IEP. Our goal is to get up to 30%, and I think we're going to reach that.
Okay, thank you.
Yeah, thank you.
I think as the Dean indicated, that is an international co-op program. And also we do have, we did not advertise, but we do have co-op like a Rhode Island DOT. Some students, they are working at the Rhode Island DOT, not only summer during the academic year. So we do have the co-op program, but we not advertise like a Northeastern.
Yeah, it's not co-op. It's simply the different terminology. It's an intern. It's more of an internship program. A DOT guarantees us, 25 slots a year. I mean, that's like your co-op program, because the Camp Joseph McKee would guarantee a certain number of spots every year for your students. DOT does that too. The other one is Newark. Newark has a student services contract, which has been in the University of Rhode Island probably since the late 80s. It was competitive, and it's a contract which is a 5-year life, and so it's been continually renewed. And in really good years with Newark, we have sent 90 students to Newark for internships over the summer. Are they Rhode Islanders? Only 30% come from URI. The other 70%, some might come from Northeastern. They come from all over the country. And we are basically the group that takes those students, makes sure that they have the classification that they need, to get into Newark's operation, and then go over there. So we've been sort of the funnel for that for 20 plus years, and we're proud of that, because Newark's proud of that, because it's been a great feeder system for Newark to get them on as full-time employees afterwards. So in a way, that's the same type of thing. So it's the IEP, it's the transportation group, and it's Newark, are the formal programs that we have. But a Pratt & Whitney will call us up and tell us, we'd like to come over and interview. Or we have FM Global, Sensata, General Dynamics. They come here twice a year, sit in this room with our seniors, and basically introduce themselves and say, all right, we'll take the applications at the end of it. We're proud to say that for General Dynamics, we're right up there in the top 2 or 3 in hirings in the last 2 or 3 years with regards to the Rhode Islanders that have been here. So.
Well, I have 5 children, 3 of them are triplets, and I gotta make sure they get a job.
No, you're right, you're right.
I gotta make sure that.
Just one quick anecdote. As we go through that process of approvals in the General Assembly in the springtime, the Speaker of the House is Nicholas Mattiello, and obviously he was a key person to agree that engineering bond needed to get onto the referendum. And what was interesting is that he stood up and made the comment that his son just graduated from civil engineering in May and had a great job at Cardi Corporation. And the comment he made is exactly what state universities are supposed to do. They're supposed to educate our students, give them a great technical background, and then we as a state need to have good jobs for them to be able to go into. And that was a classic case of that happening. I think Northeastern's great. I went to Tufts, so I spent a lot of time going over to Northeastern and Hemingway in the trolley and everything.
He got his PhD at the Penn State, and then our keynote speaker graduated from the Penn State. So today is a Penn State day.
Go Nittany Lions, yeah. Yeah. Any other questions? I thank you very much for coming, and enjoy your day.
We'll have champagne at the Saudis' pool.
I'll be there.
Okay.
All right, next on our list of speakers this morning is Senator Jack Reed, who was not able to join us this morning, but he has sent a video message which will be played.
27th Rhode Island Transportation Forum. I commend the Rhode Island Transportation Research Center and URI for hosting this annual forum. I also want to thank this year's speakers and presenters, including Mr. Kango Park, Consul General for the Republic of Korea, and Mr. Carlos Machado of the Federal Highway Administration. Finally, I want to recognize Dr. Wayne Baker, who once again leading this conference. Transportation drives our economy, and it's more important than ever that we find innovative ways to build and manage our surface transportation systems and infrastructure. For years, experts have warned us about crumbling conditions of roads and bridges. Indeed, the American Society of Civil Engineers gave us a D in its most recent infrastructure report card. We've got to do better. That's one of the reasons why I'm pushing for a long-term transportation bill that increases federal investment in transportation. But we are facing serious budget constraints, and greater federal funding alone will not be enough. We are going to need support from all sectors of government and the economy. Most important, we will need to be smarter and more innovative about the investments we make. For instance, developing material that can better withstand the rigors of traffic and weather, and adopting new construction methods that save time and money. We have seen the benefits of new ideas and what they can produce. This summer, for example, in just 10 days, Rhode Island Department of Transportation was able to replace an 87-foot bridge on Route 95 by prefabricating the new span before hoisting it into place. That strategy saved the 72,000 drivers who cross that bridge each day an enormous headache, and it saves taxpayer dollars too. This is the type of approach needed to make our infrastructure investments go farther, and it is part of the reason you are all here today. Again, I appreciate your participation and hard work, and I look forward to hearing more about your efforts and solutions. Thank you.
Senator Reed has been a great sponsor of University of Rhode Island, and every chance he gets, he helps us in the best way that he can from his position. We had also, as Wayne mentioned, the governor scheduled to come and speak this morning, but he got tied up with other matters, namely a presidential visit, so I assume he chose the president over Professor Lee. I don't understand why, but. We also had the General Counsel of South Korea scheduled this morning, but he too got called to other more urgent matters. Namely, the Minister of Science was visiting, I guess, and he got tied up with that issue. So, but third on that list of political representatives, and certainly not the least, is Representative Spencer Dickinson from the Rhode Island State House, who's here this morning to give some remarks, I guess, on the political side.
Well, at first I want to tell you that nothing more urgent than the University of Rhode Island is going to call me away from this meeting. It's a pleasure to be here. I'm Spencer Dickinson. If you live a couple of miles to the south or west of here, there's a strong possibility that I am your state representative. Wanted to be sure that my remarks were in line with the topic of the conference, and I see on the book that essentially it's summed up this way: Roadway can't fix itself. Truer words were never spoken. What I'd like to do, I do bring you the greetings of the legislature, and my colleague, Nick Mattiello, very proud to have his son graduating, and really tremendous good fortune. You know, it's absolutely true that 125 million, that is the largest bond issued. No mistake, possibly a coincidence if there is such a thing, that the Speaker's son graduated, largely because it gave the Speaker and others of us an opportunity to appreciate the university. I just want to throw out a few ideas and a few thoughts, and I think that's the difference between politicians and engineers, and I am a politician. I like to think of myself as a numbers guy, but if I'm a little bit of an engineer, it's fully self-taught. But I just want to throw out a few ideas and then leave you at the end of my short remarks with a simple request. I have a saying that I've developed over the years that applies, it seems to work very well for me. And that's and I probably didn't invent it, I probably heard it from somebody, but there are two kinds of problems. Political problems and engineering problems. And engineering problems are easy. The engineering may take millions of dollars, it may take time, and it may take the application of great minds. But there's almost nothing that can't be done with engineering. When Napoleon proposed to build a tunnel under the English Channel, the English were afraid that somebody would invade through the tunnel. So for a long time, it was a political problem. But as an engineering problem, the impossible was done, and now it's just another thought. We're talking today a little bit about the engineering college, which I'm honestly very excited about. I think and I remember in years past reading about countries in various places in the world, Abu Dhabi, what would you spend your money on? A shoppers mall? And nobody ever asked me for my advice, but I'm sure all of us would agree, the number one thing, if you were a developing nation, to spend your money on would be an educational institution based on engineering, because that's the future. And I may be just kind of wandering here a little bit, but I want to ask a question. Is a submarine a form of transportation? Well, maybe not. Maybe a B-52 bomber is not a form of transportation either. But I just want to look at the question of the 50 years that the university has waited for a new engineering college. And the 50 years, what else happened in that 50 years? What is the span of time? That's a long time. And I mention submarines because the engineering college that you are about to build is just a few miles from something that's very important for us to realize, and I'm not sure we understand it. We don't think about it very much. The finest shipyard in the entire world is right over there in North Kingstown. It's not the cheapest, and it's not it's not the largest, but it is absolutely the best. And there's a saying in the Navy, we don't talk about submarines. And now I'm not in the Navy, but I don't know much about submarines. But what I do know is that what's built just a few miles from here is different and better than anything else in the world. Think about that. So what is about to happen is that a brand new engineering college is about to be built just a few miles from the finest shipyard in the world. Think about that. I mentioned that the question of the number of years, and again, as a politician, how long do you wait for the next bond issue? People are always saying, well, gee, we just gave them something last year. They got, well, let's put it in perspective. And in terms of transportation, there are a couple of things that have struck me over the years that I remember hearing, and I hope I'm right about this. If I'm not, somebody can Google it and come up with a better. The canal system, which was built in this country, cost many lives and took a long time. It opened up entire areas of the middle of the country to transportation and commerce in a way that hadn't been done before. And there's a saying that transportation, when a step forward is made in transportation, the whole economy changes and steps forward also. How long did the canal system last? It lasted 10 years before it was superseded by rail. 10 years. Another example is clipper ships, the ultimate of the age of sail. The clipper ships lasted 10 years before they were set aside in muddy, shallow areas on our coastal cities and allowed to rot because something better came along, steam. Now that's 10 years. It took 66 years, and you know what I'm about to say. In 1903, the Wright brothers proved that humans could get in a device and fly. 66 years later, humans were walking on the moon. 66 years. 48 years? What's the difference between 1969, 45 years, and today? 45 years. That's 1.68. So in other words, the time between man's walking on the moon and today is almost as long as how long you've had one engineering college that's about to be replaced. Time is, we don't sometimes appreciate how fast the world is moving. We're stuck with one transportation we're stuck with system today we're stuck with is jet flight. I know this because I'm 6'2" and I can't fit in an airplane. In 1958, I crossed the Atlantic. 1959, I crossed the Atlantic in an airplane that took 18 hours. It had 4 propellers. The following year, the jets were introduced, and ever since then, it's been 7.5 to 8 hours. That's sort of like the story about how the B-52 bombers today are being flown by the grandchildren of the original pilots. It's amazing how time is a factor in some of these issues. One little anecdote I just wanted to share with you, and it may tie into your keynote speaker, I'm not sure. But the kind of thing that I worry about, and again, I'm illustrating the mind of the politician a little bit here. I understand that the richest man who ever lived, and that's a fascinating story to me, to anybody, I guess, John D. Rockefeller, before the automobile was invented, he was already very rich because he sold hay to horses. And he had little stores, and one of the things he sold in the stores was oil lamps, and they got some of this oil out of the ground and put them in the oil lamps, and all of a sudden somebody introduced the internal combustion engine as a means of transportation, and he was positioned to become the richest man in the world. And he did this by building refineries and getting the oil out in greater quantities to run vehicles instead of just oil lamps. And there was a byproduct, and the byproduct was this heavy, black, gooey stuff. And they didn't know what to do with it. It was all over the place, and somebody had a brilliant idea. Let's spread it all out over our dirt roads. Now, the problem comes, in my mind, when the Tesla becomes the vehicle of the present and the future. And the observation that I would have is that there aren't any byproducts from the Tesla that help to pave our roads. So that when we move to that, when we make that next step, and we do go beyond fossil fuels, what do we pave our roads with? Well, you know the answer, or you will if you don't, because there is an answer. I said I'd bring you a request, and the request is, and I know that it doesn't quite fall into the category of Roadway can't fix itself, but you know, one of the stories that we used to kind of joke about is that Al Gore invented the internet, and I don't know if that's really true or not, but I understand that his father actually did introduce the interstate highway system during the Eisenhower administration, and the concept was to build these incredible roads connecting all of our major cities. And if you ever go down through Westerly and drive on the old post road, it's that little road that sort of goes off to the side. Sometimes it's a 10-foot wide, a little piece of asphalt that loops off of Route 1. That's the road that George Washington rode his horse on. That is also the road that was the trucking artery for this country when we won World War II. And the interstate highway system and a few upgrades to the post road replaced that. But there's something missing. And one of the reasons I know that is because I have a grandchild that lives in Hartford. And I don't know if anybody's ever tried to get to Hartford, and I can tell you there are about 10 different ways, and all of them are a little bit unsatisfactory. So here's my proposition. Let's just get the darn thing built. Now, it was proposed a few years ago, and one of the issues was, and I think this does become a transportation maintenance and transportation technology issue. One of the issues was it had to go through the reservoir. Well, this again loops back to my concept of engineering problems versus political problems. That was not an engineering problem. That was a political problem because a lot of people didn't want to look at a road. And I'm sure that if you've ever built a road, and I have not, I've built a couple of driveways, people don't necessarily want to see the change. So the issue was raised, here's a good reason that we can't get to Hartford in a hurry, and the reason is because there's a reservoir, and it's very important. And by the way, don't forget, we are a rich state because we have a reservoir that takes care of 2/3 of our water needs, and there are states in this country that only dream of having that. And when anybody tells you Rhode Island has economic problems, that may be true. We are a rich state, and that reservoir is valuable, so of course you wouldn't want to wreck it with a road. But here's the problem. They had it backwards. The road saves the reservoir because drainage on that road is part of the new road. It's not existent in the old road, and every single day that road to Hartford does not get built across that reservoir is a day that puts that reservoir at risk. So what I'm saying is, let's think about it. Let's do it. Land values aren't going to get to be any less. Where's the money coming from? Gee, we're spending, the biggest bond issue we ever had is going into the URI Engineering building, so where's the money going to come from? Does anybody in this room has anybody in this room ever heard of Vinci? Well, I Googled it, and it turns out it's the largest construction company in the world. And wouldn't you know, it's in France. Well, let me tell you what they do in France. If they need a road, and you notice this if you're a tourist, you go there, there's no road, you come back a year later, there's a road, or a tunnel, or something. The way it works is Vinci builds the road. No bond issues. They just build it. The only catch is they get to decide how much the toll is. And they set the toll to match the maximum use. If $17 is too much, it's $16. Now, would I pay $17 to get to Hartford? In theory, I would not, but in reality, I would. And by the way, when you design that, and I know that this is about the road can't fix itself. Well, the road can't build itself, and I'm sure some of the same people fixing roads are going to be involved in building this road. And one of your graduating classes is going to leave that brand new building, and they're going to build that road. Now, they may do it 50 years from now, long after I'm gone, or they may do it soon enough for me and my wife to benefit from. But here's the little detail I just want to point out. Many years ago, they built a road from DC to Dulles Airport. They fortunately left a median strip. Now there's a fast rail on the median strip. So when you build that road to Hartford, make it a straight line and give us the possibility, and matter of fact, it wouldn't even be a bad idea to kind of draw it into the design for a fast rail so that you can get on the train, or whatever it's going to be called when that time comes. Hopefully it's soon enough that we'll still be calling it a train. You'll get on the train in Providence, and 20 minutes later, you get out in Hartford. Now, how does that change the economy of Rhode Island? That is a leap forward in transportation. Providence now is a crossroads because the rest of that crossroads is the ocean lanes to the entire world. And instead of Route 295 just being a little loop, it now becomes a little bit more like the industrial Route 128, which is a wheel that has spokes. Route 295 is a wheel without spokes. And the spoke that's missing is that real serious road to Hartford. And if I could kind of wrap it up by saying maybe we ought to think about getting it done sooner than later, because what happens if we haven't built it and we run out of that black gooey stuff before we do? Thank you very much. I appreciate the chance to be here today. And I will read this book very carefully.
Okay, so if you look at your program, we had next on the list Greetings from federal agency, but I understand Mr. Carlos Mercado was not feeling well and was not able to be with us. Then we also had Mr. Timothy Scanlon from the Rhode Island, I guess they changed their name. Wasn't it these, didn't it used to be Rhode Island Construction Industries?
Construction industry of Rhode Island.
Construction Industries of Rhode Island, who's been a longtime sponsor of this event. You know, I've had the good fortune of being involved with this for almost 11 years now. Since I came to URI, Wayne has always invited me to come to this forum. And when I was able to, I've always attended it. And I know that putting this forum together, you know, this is the 27th forum, but it's actually 22 years that it's been in place. And Wayne Lee started it, and he's been doing this every year of those 22 years. Some years, I guess, he had 2 forums in the early years, and then it went to an annual format. And putting these kinds of things together is not so easy, and it takes a lot of time, energy, and a lot of effort to bring this together. And Wayne has been persistent in those regards, and this is his passion, so he does it every year, and without him, I don't think we would have such a thing, such a forum at University of Rhode Island. So he's an important player. He's had good support from the construction industries of Rhode Island, I think for most of those years. And it's unfortunate that Mr. Scanlon couldn't be with us here this morning, but I would like to introduce Professor Wayne Lee, who is the champion of transportation at URI.
This big hand is for Professor Aram Nashasharif. As some of you know, he was my former boss, grand boss, and then become good friend, and then now he's leading our faculty as a president of faculty senate. So we really appreciate your coming and convening this forum with your busy schedule. Okay, let's give him one more chance. Thank you very much. Yes, my time is very short because we have 2 wonderful speakers, Dean Ray Wright, and then Representative Spencer Dickinson. So what I'd like to do will be, I will just recognize some students who contribute to our transportation program. So if you look at your the handout or proceeding, the second page at the top, I want to recognize first the Rhode Island Transportation Research Center Fellowship recipient. One of them is A.J. Singh. If you don't mind, could you stand up? Give him a hand. Thank you. And then Kiyoshi is walking outside. And actually the A.J. is working on computing system today. So without him, we cannot move on. So it's a very important person. Second recognition will go to special group. The Holy, as you can see, so the name is there, the second there. Holy Faubert and Patricia Hogan, Lesson Shepherd. Those 3 students, they participated in the International Long-Term Payment Performance Contest. And they won the 1st place. The news came last week. And then luckily we have at least 1 of 3 here. Holy, could you stand up, give him our big hand? Thank you, Holy. Okay. Tracy and then Nelson are not here. The reason is they are IEP students. So they are in now Spain. So they are spending 1 year intern or study in Spain. So they are not here because obviously I don't have enough money to invite them to come here. So Holly is representing those groups. And also I'm very lucky to have our special engineer in our state. Rhode Island DOT pavement engineer, Paul Peshing is here, right? Could you stand up if you don't mind? Please give him a hand. And the reason I'm introducing him is when the 3 students worked as a summer intern last summer, the Paul was the supervisor of those 3 students to write a paper. And I think we in depth to you big, okay? Sometime we'll invite for separate, okay? And also, some of you have opportunity to ride the train from Wickford to Providence or Boston, right? How many of you ride the train? Some of you do, okay? When Paul Passing was pursuing his master with me, master program, he designed that Wickford, the parking lot and then station, also the Kingston as well. So sooner or later, we'll have extension from Wickford to Kingston. That's what Paul did. I really appreciate your foresight and then also contribution to our state transport system. The third recognition will go to NSF Minority Undergraduate Fellowship. The Tommy Oyakan, most of you saw him because he was at the residence desk. And also we have Kenny Oladoso. Those are 2 students, 2 undergraduate students. They are getting the fund from the NSF. Actually, that fund came to College of Engineering, and then we are fortunate to receive those 2 students. And then they are working in transportation. And the next recognition will go to the recipient of Narragansett Improvement Company Scholarship. About 25 years ago, the owner of Narragansett Company, I had the chance to meet with him, and then he donated at that time $100,000, and then we are giving the scholarship with that fund. So that is, I think this year we gave 1, 2, 3, 4, 5 students. Same time, the Hudson Group company, they also donated $100,000 about 15 years ago. And then we are giving the scholarship to 5 students. They are all transportation company, basically pavement engineering company. So Holly also got one of those scholarships. Congratulations to you again. Right? All right, and the team, Scanlon, who is the executive director of construction industry Rhode Island, supposed to be here, but he tied up with the bond issue again, so he will come after lunch. So at the time you will see. What he want to do is he's going to establish Henry Sharrock Scholarship, who was predecessor of team. So we'll have another the scholarship who will study pavement and then transportation engineering. I have the presentation, but it will last only 2 hours, so I don't want to bore you. So I will cancel that, and then I'll move to the next program, if you allow me to do. It's okay? All right. Well, no objection, so I'll move there. So now we are coming to real meat of the program. Before introducing our keynote speaker, we have one, I don't know it's appropriate saying or not, rising star. The Professor Aaron Bradshaw, he conducted a research program for Rhode Island DOT, and then he's going to make a presentation about resilient modular's behavior of reclaimed asphalt pavement aggregate surveys brand. So please join me welcoming Professor Bradshaw. Hey. You have,
Thank you.
okay, you have that.
Yeah, just have to kind of switch.
One of the reasons I invited Aaron is something related to our keynote speaker. So we want to have an interaction between Rhode Island and then the United States. United States of America, whatever, nationally or regionally.
Thanks, Professor Lee. It's an honor to be here to talk about some of the research that we've been doing over the last year or two here at URI. The previous speakers really are looking at a very big picture, and I just sort of want to take you down to a much smaller world here, and that is the world of, I guess, pavement design, specifically the foundation for the pavement design. Just to let you know, my background's in geotechnical engineering, excuse me, and specifically actually on the laboratory study of soil liquefaction. And so when, after having that experience, I noticed in pavement design, soils go under cyclic loading from traffic. It's in a very similar way to the way they do under earthquakes. So there was sort of a natural connection to start to work on some of these problems involving traffic loading. I also want to acknowledge Jeff Costa and Joe Giampa. Jeff is obviously out working now, and Joe's a current PhD student, and they did all of the testing for this study. I also want to acknowledge the URI and Rhode for funding this research. And this will be a fairly quick overview of what we've done. I'm just going to give you some background, the motivation for the study, how we actually performed the study, the results, and some conclusions. So just to give you some background, currently pavement design is shifting. Traditionally it has been done empirically, and it's now in the process of moving more toward a mechanistic-based approach for pavement design. Many states have already sort of made this transition into the more mechanistic approach. Rhode, I think, as far as I understand, is sort of in that process. And so Colin Franco from Rhode approached me and asked and said, hey, one of these important properties to be able to design pavements is this thing called the resilient modulus. And at the time I didn't know what that was, but come to find out what it actually is the Young's modulus. You could think of it as the Young's modulus under cyclic loading. And so it's this property, it's the stiffness of these pavement structure of the various layers, including the subbase and the subgrade soils that contribute to how that pavement ultimately is going to perform. So this parameter is really important. The other thing that we discovered is that generally the base of an asphalt, so if you look to the far left, we have the asphalt layers, and typically below that you have virgin aggregates. So you have rock-based aggregates, and those are what's traditionally been used. And what we discovered is that, hey, what actually happens is you can replace some of those virgin aggregates, which are more expensive, with these things called reclaimed asphalt pavement aggregates. And basically what that is the asphalt layers sort of ground up into particles, and then those are used as materials. And that's really an interesting practice, because that's sustainable, and that you don't, what are you going to do with this asphalt pavement once it's sort of lived its life? And so what do? You grind it up and you use it for the next go around. So that's an appealing, sustainable practice. The only issue is that as we keep doing this, and so what I'm showing you here is on the 1960s, we had the virgin aggregate, 1980s. Practice might have been to mix in some of these wrap in with the virgin aggregate, so that's now at about 25% wrap content. And then now recently, this was actually at the Route 165 site that they just recently did. And now what they did is they took the asphalt in the wrap aggregate subbase and did a full depth reclamation and combined all those, and that gives you a new one that's now 60% wrap. So from what I see is there's sort of a trend, if you keep going back to these roadways and keep reclaiming them, the wrap content keeps going up. And so that may not be a bad thing, but we want to make sure as engineers that if we're going to continue to do this practice, we want to be aware that well, how is this going to affect performance? It's sustainable, it makes sense economically, but is the performance still going to be adequate, or at least we can design around what's going to happen. So what I'm showing you in the profile to the right is you a couple of things. You have at the bottom, you have some of the old 1980s wrap aggregate subbase. So that's already been in place for 30 years or so. And we want to and it's going to keep going. And then you have the new stuff there just above it. And so this particular project gave us an opportunity to take some samples of that subbase and see how it would perform in a resilient modulus test and sort of see where things go. So what we did is we looked at three things. We tried to figure out is aging going to affect, how the aging is going to affect that 1980s mixture. Has it improved since 1980? Is it going to continue to improve, et cetera? We wanted to figure out if you did a full depth reclamation, how is that going to change the subbase? Is it going to make it better? Is it going to make it stiffer? Is it going to make it weaker? Is it going to strain more? And then the final one is when you do a full depth reclamation, it's common practice to add stabilizing treatments to it, such as calcium chloride, asphalt emulsion, and Portland cement. And we wanted to see, did these things contribute? How do they contribute to what's going on? Again, in terms of two things, in terms of the resilient modulus and also in terms of the permanent strain. By the way, permanent strain is related to rutting, right? So if the soil continuously deforms, that's going to ultimately manifest as a rutting type at the surface. So what did we do? We took some equipment that Professor Lee developed in the 90s, and we sort of gave it a new brain. So we have all the sort of hardware and stuff, and we got an upgrade on the computer and the software. Again, funding provided from URI and Rhode. And so what we do is we prepare a sample here, a specimen that's 6 inches in diameter, a foot high, and then we subject it to cyclic loading. And a typical stress strain curve is here on the left, and you see we do there's different stages of confining pressure that's applied, and then various cycles. And then you get the resilient modulus basically by taking the slope of one of those loops, and it's generally done toward the end of the stage, about the last 5 cycles. The other thing that's done is the results that come out of the test are fit to a material model. I'm showing just an equation here on the right. Really all you're trying to do is find 3 parameters that make that model fit, and in the design of the pavement system, the engineer will input those 3 models for a specific layer. And so what we wanted to do is make sure when we did all this, we gave some practical parameters that someone could use for pavement design, i.e. Rhode. Just to show the 3 questions we were going to address, I just want to show you a figure for each of those just to give you a sort of a sense for the results. There's a lot of things going on here that I'm not going to be able to cover. The first one is the resilient modulus appears to increase from aging. Now, how do we figure that out? Well, we had a sample that we collected that was put down in the 1980s. We brought it back. Now, we didn't take an undisturbed sample. We recompacted it in the lab to 95% of the maximum unit weight in a modified proctor test, which is standard practice. Then what we did is we took some data that Professor Lee collected in 2001, and those were the solid lines were virgin aggregates, and then the smaller, thinner lines were different wrap contents. And so what we assumed is that's the young, we call that the young wrap mixture, and then our blue dots there are the old or the 1980s. I got to be careful. I was born in 1972, so I guess I'm old. That's the old wrap mixture, and that's about 25% wrap content. And you notice if you look on the contours, the resilient modulus generally falls above the 40% or so wrap content for the young. So now this is not, now ideally what we'd like to be able to do is test the sample when we first make it and then wait 30 years or so and test the second sample, but that's kind of a tough thing to do. So this was our way of sort of addressing whether or not things are getting better or worse for us. And it shows that the resilient modulus appears to be going up. And so that's just sort of an indirect way of trying to figure that out. The second thing we wanted to do is figure out the subbase that was there, again, the 1980s subbase, and now we went in and we did a full depth reclamation, which means the wrap content went up because you're mixing in that asphalt layer now. And you can see by the plot here, the 1980s subbase is the black circles, and then the new full depth reclamation is the squares, and that's about 76% wrap content. And the key thing here is, on average, it appears that the subbase is stiffer relative to what it was. So the new construction produced a stiffer subbase. The problem is, though, the permanent strain doubled. So it got stiffer, but it's now more susceptible, I guess you could say, to rutting, to permanent strains. The other thing, to answer the third question, the different treatments, what we did is we took some sample of that full depth reclaimed material. We did some tests with no treatment. That's shown as the black circles there, solid circles down at the lower end of the figure. And then we did some tests where we had cement, and we waited 4 hours and tested it. We added Portland cement and waited 7 days. That's the diamonds. We also added asphalt emulsion to the sample and tested it. That's the blue triangles. And then we also added calcium chloride to the specimen. That's the blue squares. And you can see that the asphalt emulsion and the calcium chloride are kind of plotting in around the same area where the untreated samples were. And right now we don't have a large data set to be able to distinguish statistically whether those changes are significant. But right now it's looking for, if you sort of look at the typical uncertainty with the test method, it's sort of all falling within the scatter, I guess you could describe it as. So what we're not seeing is this improvement or modification due to the, as far as resilient modulus, due to the addition of calcium chloride or emulsion. However, the addition of the emulsion actually made the permanent strains larger. Okay, so things appear to be not maybe changing modulus, but they are affecting the permanent strain. So just that's sort of something to sort of keep in the back of your mind as you're designing these things with these wrap mixtures. The Portland cement, however, had a huge effect. The 4-day cure time, that's the solid diamonds there. That was really to model what happens is when they do the reclamation, they might just close the road for 4 hours or so and say, okay, now we'll open it to traffic. So we wanted to get a sense for what that would happen under that scenario. And then if you allowed that thing to cure, 7-day cure, what would you get? And you can see this clearly a significant increase in the stiffness, because essentially you're cementing the particles together. And no surprise, the permanent strains are cut in half when you do that. Okay, so just to summarize briefly what we just found, resilient modulus appears to increase from aging. Again, that was not looking at the same sample. It was using data from young, quote unquote young, and our samples that we recovered that were 1980s vintage. Resilient modulus and permanent strains increased after full depth reclamation. Okay, it got stiffer, but it strained more permanently. The calcium chloride emulsion treatments, not much influence on resilient modulus, but clearly increased the permanent strain. Cement treatment increased resilient modulus but reduced strain. And then at the end of all of this, what we also provided is a data set that someone that does this for a living and is designing these roads can use these parameters if they wanted to sort of look at design scenarios. So I hope, is it Paul in the back? I hope you find any of this interesting or useful to you.
I'm just wondering if you tried pulverization without any cement treatment or
Yep.
emulsion treatment.
It was, no, we did not.
Okay.
No, we did not. but so one of the things I sort of want to leave you with, this, for us, this was new, it was a start. And so we hope to, now that we have this equipment, to work with Professor Lee and try to keep this going. So if there are issues, Paul, that you identify that would be helpful to improving the design practice, then that's what we're here for. You know, we're here to help and to make things better. Yes?
Is there a road in Rhode Island where they're doing this?
Doing.
Doing the process where they're having the old?
Yeah, this is from Route 165.
165?
Yeah, this is the actual, I mean, it's an illustration, but that's essentially what happened.
All right.
Yeah.
165.
Yeah, and I think we're, well, you know, as I said, well, I didn't, as someone said before, you know, yes, we could be building new roads and we should be building new roads, but I think maybe most of the work right now is, you know, fixing roads and revitalization and replacement, and so this is kind of a, you know, reality sort of right now.
That road was done about 25 years ago, and now we did it just this past year.
Okay. So what's the typical life, Paul, about 20, 25 years, is that?
20 years,
Yeah. Any questions? Any other questions? Thank you very much for your time.
Thank you.
Before you leave, there was just one question.
Yes.
Is there any difference when they use different types of tacks between the two layers, back and down? Is there a difference in the tacks? Have they tried different tacks?
You know, that's sort of beyond my understanding. We sort of just looked at the performance of the unbound subbase and how it material properties. I haven't looked at the system or how the interfaces are or anything like that. Is that what you mean?
Yeah.
Is the system? I haven't looked at the system at all, and it's really not. Maybe Professor Lee could answer that question.
Oh. Okay, thank you.
Okay, sorry.
Okay. Yeah, thank you again. Route 165 is the one, one of my doctoral students, Kate Wilson, is in charge. She is also the Rhode Island DOT engineer, working with Mr. Patching very closely. And then, as you can imagine, now we may not need a new highway. We have probably enough, but we have to maintain. And then the pavement is not going to last forever. It has probably 20 years for the asphalt pavement, even less sometime, right?
20 years.
So, 4 years. I know. One of the reasons we have that very short life in Rhode Island, unfortunately, we have not designed pavement structure properly. Rhode Island DOT engineer know, but the front office, is whatever reason, they said that they are designing, but actually they didn't. So what we are doing is we try to assist, we try to work with Rhode Island DOT, and then working constructively, not to have any different view. So Kate Wilson decided to develop 4 options for the Route 165. So actually there are 5 test sections, 1 control and 4 different ones. So 1 was with the emulsion, 1 was with the cement, 1 is with the geogrid, and 1 is calcium chloride. So we have to evaluate which one is the best for Rhode Island environment. But unfortunately, the front office of Rhode Island DOT, they did not support the URI yet. But luckily, fortunately, they partially supported Aaron Bradshaw, at least determining those resilient modulus. So he just started. So in our kind of, we cannot do everything same time. We need piece by piece. And then sometime probably we need to get together. So myself, I'm in the position to promote junior faculty or Rhode Island engineer to right direction. It cannot be changed like 1 year or a few years. It will take maybe 10 years, 20 years to change those things. So someday, in Rhode Island, we are going to design pavement structure properly. Someday, I don't know when, okay? There are lots of politics there, so I do not want to get into those. So, but university, academia, we should be ready when the opportunity will come. That's what we are doing. That's why we built those testing systems. I built that testing system about 20 years ago. And I did not get the fund from Rhode Island DOT. I got the fund from New England Transport Consortium. And then when the Aaron Brothers show joined, I gave it to him, okay? And then you upgrade and then work for Rhode Island DOT, whatever, and then do more. Do not stay whatever we have done. Move on. So someday, and your question about the system, the interaction, all those things, is very, very important. But without funding, we cannot do that. As you know, the main function of a college professor is teaching, educating students, or training the future workforce. That was the number one criteria. And then if that opportunity arises, and then we do research, which is ideal, but sometimes it works, sometimes it does not work. When I came here to university, I had a wonderful relationship with the Rhode Island DOT, and then we had lots of work done. But recently, something happened, so I'm kind of not spending too much on research, but someday, it will be better, someday. Okay? I hope I'm kind of answering your questions.
Yes.
Okay, good. All right, so everybody waited until this moment. We have here our guest speaker, Dr. Brian Crowell from Auburn, Alabama. He, as I briefly mentioned, he went to Penn State for his Bachelor of Science program, since he was a resident of Pennsylvania, I believe. And then he moved to Virginia Tech for the Master of Science program. And then he worked for Virginia DOT and University of Virginia. And while he worked for that organization, he also pursued his PhD from Auburn University, Alabama. And he received his PhD from Auburn University. And and then his wife established one consulting firm, and they work very hard. Actually, one of the leading research company in pavement engineering. Same time, we have a very distinguished organization, so-called Association of Asphalt Paving Technologists, AAPT. The Dr. Crowell is serving as the president of the organization. That's quite an honor and quite a leadership. With a busy schedule, he was able to come and then give a talk about the pavement engineering again. Please join me welcoming Dr. Brian Crowell.
Good morning. So we have almost a half a century now of recycling pavements. It was really with the oil embargo in the 1970s that recycling asphalt pavements kind of gained prominence. State Representative Dickinson mentioned that there's political problems and engineering problems, and I guess the oil embargo became a political problem. And one of the solutions to the engineering problem was the milling machine, the development of the milling machine, which enabled us to quickly and easily reclaim asphalt from the pavements. Initially, only limited amounts of the material were used, or higher amounts, and then it's changed. The amount of RAP that's been recycled into new asphalt's changed with time. But with the gas prices you've all seen, again, State Representative Dickinson mentioned with a Tesla in the future we might not need oil. Well, we've all seen now that oil companies are trying to extract as much gasoline from oil as they possibly can. Not only have gas prices gone up, but that's resulted in asphalt prices going up because there's less of that residue left with cracking units and distillation units. So there's been an increased or renewed interest in higher percentages of recycled asphalt pavement being used. Kind of where's Rhode Island? Rhode Island allows up to 30% RAP, reclaimed asphalt pavement, in their intermediate and base courses, and they want the final grade to meet a PG 64-28. Now, this is actually a picture of a relatively new asphalt pavement in Alabama, and hopefully you can see it from where you're sitting, but there's some cracks that have developed. And as we've gone to using higher percentage of recycled asphalt pavement, that's something that can certainly occur. And it's part of the systems concept that was being talked about. If we have thin pavements, maybe some of you live on a road that's been surface treated, very, very thin asphalt pavement, less than an inch thick, but it kind of acts as a flexible membrane. When we get to I-95, you have a thicker asphalt pavement, very stiffer structure. Somewhere in between, somewhere in that 4 to 6 inch thickness range is a change in how that pavement system performs, and going from a very flexible structure that needs to deform to a stiffer structure. And so I think we need to recognize that systems approach when we're looking at these recycled materials and how much we can use in a mixture and what it does in terms of stiffness. In this regard, FHWA just sent out a memorandum in October that said recently there have been an increasing number of state agencies reporting premature cracking in new asphalt pavements. And the similarity in these pavements has been high percentages of binder replacement. So what I'd like to talk to you about today is that you can make good performing pavements with high, and you'll see how high percentages of recycled asphalt pavement, but it takes some engineering. It can't just be kind of dumped in. So what are the challenges really? Well, how many of you have ever designed an asphalt mixture? Oh wow, okay. So not a lot of you. So all right, so I'm gonna have to kind of explain as we go along a little bit. But there's different properties. We design asphalt mixtures on a volumetric basis. We want to have enough space between the aggregate particles for the asphalt. One of the things that when you grind up the asphalt, you create more dust. That dust fills some of those voids. You need something to offset that, and that's usually clean, angular materials. How you compact it in the laboratory also affects how much room you're going to have to design or put in new materials. One of the problems is low temperature. As the asphalt ages, as Professor Bradshaw talked about, it does get stiffer, and that becomes a concern in terms of cracking, both low temperature, thermal cracking, winter cracking. You might see big transverse cracks across some of the roads in the New England area, low temperature type cracks, and also intermediate cracking like I just showed in the picture. And then Professor Bradshaw also mentioned if you add some additional components to these mixtures, you can actually increase the tendency for permanent strain or for rutting. So it's how you balance all those. In looking at what really limits the amount of RAP use, there was a survey done when I worked in Virginia by my mentor, Richard Schreck, and out of the contractors at that time, 10% said that what limited it was the state specifications. 34% said it was changing binder grades because they only have so many asphalt tanks at a plant to put them in, and then 58% said it was the dust. So those are some other challenges we need to address. How many of you know what SuperPave is? All right, a few more people there. SuperPave is a mixed design system that came out in the 90s. I implemented the SuperPave design system in Alabama, or in Virginia as part of my work there. SuperPave didn't include a lot on recycled asphalt pavement. There was work done afterwards by a Mix ETG expert task group by FHWA that tried to give guidance on what percentages and what binder's the liquid asphalt that gets added and what the stiffness of that should be. Up to 15%, you can just you can literally dump it in probably. 15 to 25%, you need to start engineering, looking at the binder grade, the interaction, the stiffness of the aged material and the new virgin material that you're adding. And then over 25%, you need to blend it. This is actually some binder test data on recovered aged asphalt. The S is a stiffness value and the M is a relaxation coefficient. Basically, asphalt's a viscoelastic material. So as a strain is applied to it, say as it's getting colder out and the pavement wants to contract, it can actually relax. It can relieve some of that stress, and that's what the M value is for. There's a maximum stiffness for low temperature cracking and a minimum M value of 0.3. And what this data is really showing is that up to 35% RAP, the recovered binders from Virginia in this time period when I was doing this work, met that criteria for a -22. Testing's done at -12. -22 is a common low temperature test parameter. That's in degrees centigrade, so it's about -7 degrees Fahrenheit. Relatively cold weather that the pavement can withstand. So you can add a fair amount of recycled asphalt pavement to a mixture and not affect your low temperature properties, which is a concern in many areas. So if you're not using a softer asphalt to prevent thermal cracking, what are you using for? And maybe it's, again, looking at that membrane effect, the stiffness of not having too stiff of a mixture that it's still a flexible pavement. The fatigue parameter that's measured on binders is affected by both the high and low temperature. There's a couple ways you can do that. You could bring in softer binders. There are also products called rejuvenators, which can be used to renew the asphalt. And we'll talk a little bit more about them. So when we actually do this, we can run the tests on the aged material, we can run the test on the new virgin material, and then we can blend those and figure out what percentages we're allowed to do, or what we combine, and how much RAP we can put into a mixture. And this is some data from a contractor in South Carolina that we work with. The grade of their binder, so for instance in Rhode Island, your desired binder would probably be a 64 -28 for a standard road. You might want a stiffer binder like a 70 -28 for something like I-95 or an intersection. 70 is the temperature degrees centigrade that it should be resistant to permanent deformation in the summer. -22 in our case in the south, or -28 here, is the temperature in degrees centigrade it should be resistant to cracking in cold weather. As it gets older, the RAP, and this is by size, broken on the 4 sieve, gets stiffer, 82 -16 for the coarse RAP, 94 -16 for the finer RAP. So it's lost low temperature properties. It's not as good of a low temperature. It's actually good to a high temperature. And then one of the new things where people have looked at adding is RAS, which is recycled asphalt or reclaimed asphalt shingles. And it's actually up on the 234 range, plus 32. So a very, very stiff material. And so stiff, in fact, normally, asphalt's a relatively pliable material at room temperature. This was kind of a lump of the material that we recovered. Very, very stiff. In fact, this was a picture that was sent to me during the testing, and the person that recovered it said, "What am I going to do with this? I can't really test it." Simple equations to do the blending. In this case, with the data we had, we could add up to 29% RAP to the mixture without increasing a high temperature grade. It's just an example of the calculations you can do. Instead of just using a prescription or a methodology, say add this softer grade, do something, you can actually calculate these and blend them with your materials to adjust your grades and stiffnesses. Well, what happens if you soften the binder, but the mix still has poor intermediate cracking resistance, kind of the everyday fatigue type cracking? What else can you do to improve it? What you can really look at is the effect of asphalt. One of the big issues with using old asphalt is how much of it really reblends. When we test it, when we extract the asphalt and measure the asphalt content, we assume that all of the old age binder mixes with the new binder and everything becomes homogeneous. And the reality, that's one extreme. The other extreme would be that those rocks, those reclaimed materials, just act as black rocks, that none of that old binder comes off and reblends. So the reality is it's somewhere probably in between those two, that some of it comes off and mixes and some of it does not. And that's really knowing how much of that is effective in bonding and gluing the road together. There's a procedure in AASHTO, the American Association of State Highway and Transportation Officials, where you can look at binder contribution for shingles. You can also apply that technique to wrap mixtures, and basically with the same gradation, same aggregates, you determine an optimum binder content, optimum fluids content if you're more of a soils person, how much asphalt to add without any of the recycled materials, and then determine it the same way with the recycled materials. This is another example of some of the work we did in a design process. The first two lines are, I'm losing my mouth, there we go. The first two lines are material where we took the wrap, the aged material, we extracted off all the binder, and then we remixed it with virgin materials. And so 4.67% asphalt gave us 3.7% voids. That's pretty close to optimum, passing voids in mineral aggregate. We do that same lab mix with the wrap. We get lower voids. We get 2.6% voids, and our VMAs drop. If we actually run it through a plant, it's hard to get exactly when you're running through a plant the asphalt content you want. We were slightly high. We're again at 3.2% voids. And so what we concluded from this was that we actually plotted using the two asphalt contents for the lab mix that at 4.8% asphalt, basically what we had when we ran it through the plant, we should get 3.2% voids, and that is in fact what we got when we ran the mixture through the plant. So through the plant, in this particular case with 25% wrap, we were getting about 100% blending of the old and new binder. But oftentimes you don't get that, and what do? And that becomes a problem in getting these pavements not to crack prematurely and to perform well. One of the things you can actually do is lower your design voids. In many cases we design, or the normal process is design at 4% air voids. You want some air voids space in the asphalt mixture so that when it gets hot in the summer, the asphalt expands. It has some place to go other than bleeding to the surface of the pavement. If you go to lower voids, you're taking advantage of the fact that these recycled materials are stiffer, so they're more resistant to permanent deformation, and coming into a balance in between. A colleague of mine, Alan Cooley, when he worked for the National Center for Asphalt Technology and then later on for Burns Cooley Dennis, they did work for the city of Overland Park in Kansas that uses a lot of recycled materials and had a lot of premature cracking. And what they did is they came up with a tiered approach of lowering the design air voids as they increase the wrap content. So you'd basically add more virgin new asphalt as you went up in recycled to kind of counteract or adjust for that percentage that wasn't effective. More recently, a number of state agencies have developed what they call balanced or performance-based mixed design approaches for using these recycled materials. And I really think this is where we need to go in the future. One example is New Jersey DOT. Tom Bennett there, a friend of mine, helped design this. It's for high recycled asphalt pavements. Basically, their contractors wanted to use more wrap. They're milling it off the roads. They take it back to their plants. They need someplace to store it. They're running out of storage place. They'd like to use more of it in mixtures. And plus, it really is beneficial to the owner if done properly. New Jersey DOT, the owner, is willing to use that. They'd like to save the money, but they don't want to sacrifice performance. They want to balance cost and performance. So they want to get, they want to get what they need to get a good performing road. So in the New Jersey's high wrap specification, they're requiring actually a minimum of 20% wrap in the surface mix. Right now, Rhode Island doesn't allow wrap in the surface mix, and then a minimum of 30% wrap in the intermediate and base. Right now, Rhode Island has a maximum of 30% wrap in intermediate and base courses. And basically, they'll allow you to design at different air void levels. They do have a minimum voids in mineral aggregate for durability. They'll allow you to use different grades, whatever grade of binder you need to get the performance properties. But they have two properties that they're measuring. One is with the the asphalt pavement analyzer, which is a rutting or a permanent deformation test. They have maximum rut depths depending on whether it's a surface course or intermediate course, and whether it's supposed to have a PG 64 minus 22 or a stiffer PG 76 minus 22, which is used for high traffic areas. And then they have an overlay tester, which is a cracking test. They have a minimum number of cycles it needs to survive. So they're trying to balance rutting and cracking performance. And then they give the contractor freedom after that to do a number of other changes to get that performance. If you've never heard of the overlay tester, it was developed in Texas. And basically what it's simulating is if you've overlaid a concrete pavement. So in concrete pavements, we tend to have joints. As temperature changes, those joints open and close. And that opening and closing, as you might imagine, can cause cracking to propagate through the asphalt overlay. And so this test is basically the number of cycles that asphalt slab can survive that opening and closing of the concrete before it'll crack through. So it's a triangular motion. It opens to a maximum, closes up, keeps doing that until it propagates a crack. Number of other agencies have developed balanced performance type design procedures for recycled materials. Texas is one. They're kind of the originator of it. Fuji Sal there uses the Hamburg wheel tracking test for permanent deformation. Also looks at moisture sensitivity. And the Texas overlay tester. Louisiana, Louis Muhammad has put out a procedure that Louisiana DOT is looking at adopting that again uses the Hamburg wheel tracking test and the semicircular bend test, which I'll show you more of in a second. And then Wisconsin DOT, which currently allows fairly high percents of recycled asphalt pavement, is looking at the Hamburg, the semicircular bend test. And they're also concerned about low temperature cracking there because it is a colder state. This is just an example of, we're talking about adding additional virgin asphalt, how that can help, how that affects the overlay tester. This is some work we did on a mixture with 20% wrap and 5% shingles. At the optimum, so 4% voids, we said would be the typical design void percent. It didn't survive one cycle before it failed. Excuse me, that actually was not tested. We increased the asphalt content 0.6%, went to 1.9% voids, a volume of effective asphalt that matches what Burns Cooley Dennis recommended for the city of Overland Park. We got 8 cycles to failure, not very good. And then we went up another 0.3 asphalt, 0.9% voids, very low void content. We need to be concerned about rutting. We need to look at that also. We went up to 195%. So as we replace that asphalt that's not effective, we're able to offset that and improve the performance of the mixture. As you might imagine, if we're comparing different treatments, somewhat like Professor Bradshaw was showing, sometimes if you have variability in the test and that overlaps, it's hard to distinguish whether something's really improving or not. And that was one of our problems with the Texas overlay test. At times when we're getting 8 cycles to failure and one sample went 2 cycles and one sample went 20 cycles and what have you, we had difficulty discerning whether things we were doing were actually improving performance. So we looked at an alternate test, the semicircular bend test. This has actually been around in Europe for a while. Dr. Louis Muhammad at Louisiana Transportation Research Council has been promoting it recently in the United States. One nice thing about this test is it can be run with relatively simple equipment. Basically like a Marshall press that Dr. Lee's lab has, my lab has, most contractors have, performed at room temperature. But it does use fundamental engineering mechanics. It uses a J integral, which is a fraction mechanics property, as a measure of cracking. That's a picture of the test. Basically, you run a half moon-shaped sample that has a notch in it, and you propagate a crack through it, which you can see up here. You get basically an area under the curve. So you're loading it. This first slope would be sort of a Young's modulus, if you will, load versus deformation. Once you reach the peak load, we determine this area, and that gives us a fracture energy. And then we'll plot the fracture energy versus the knot depth, and that basically gives a resistance to fracture parameter, which is the slope of that line, and that's what we're actually looking for. That's our test value. Based on field pavement performance, Louisiana came up with a proposed criteria of a minimum J integral value of 0.50. This is just an example, different mixtures that we've looked at. Just pointing out a couple. I mean, we had mixtures here, some with 25% wrap, 5% shingles performed obviously poorly, below the 0.5. We actually have a 100% wrap mixture. I'll show you more that perform very well. A number of typical contractor mixes here that also perform very well. So it's possible, very possible, to get good performing mixes. It's also possible to get poor performing mixes. Real quickly, if you're working in the lab, how you deal with wrap. For Rhode Island type quantities, we just recommend air drying the wrap, not putting it in an oven, so you get additional aging, splitting out, trying to get the most representative sample, like with any materials. Representative sampling is important, and then placing in the oven just 30 minutes prior to testing. For higher percentages of wrap, you really need to do something different though. When you run through a plant, the wrap's not dry when you put it in. That's kind of the whole purpose of running it through the plant, is to dry it and heat it up. And the moisture that's liberated as it's heating actually helps that mixing process. So what we've been doing is looking at taking mixture or wrap at basically it's the moisture content, it would be in situ in a stockpile, and then adding superheated virgin aggregate, which is the same thing you do in a plant. You overheat the virgin aggregate and then mix it with the wrap, and there's a heat transfer process. The steam that comes off the wrap at that time actually helps liberate some of the asphalt binder. Kind of to give you an idea of the temperatures, if you're adding 20% wrap to a mixture with 3% moisture in it, you'd be looking to get a 300-degree final mix. You'd have to superheat your aggregate to 389 degrees. So it's quite a bit of additional heat that you add above your mix temperature you'd like to have at the end. A little bit about processing wrap quickly. How you treat the wrap is going to affect how well it'll work in a mixture and perform. One of the key things is you don't want to create more dust. I mentioned that was a challenge. You really want to break the asphalt bonds and not the rock. In the past, common practice has been to size all wrap to a -1/2 inch material, crushing any rock larger than that. So if you have base mix coming in with 1 inch rock, you'll run it through a crusher, crush that rock, make everything 0.5%, -1/2 inch. That creates more fines, which are problematic. You do need to watch out for deleterious materials. You might see tires and things along the road. If you're driving along the road, you need to get these off, preferably before you mill the road. If they get milled up and end up in the wrap and you don't catch them, you can get inclusions like this in the pavement. I looked at a pavement in a state I won't name that had some, 30,000 spots like this. And we found a treatment process to mitigate it, but it wasn't easy. Many people are fractionating wrap into a coarser fraction and a fine fraction to give you more control, just like you have different virgin aggregate sizes. Coarser fraction has less surface area per unit mass, so it'll have lower AC content. It also has lower -200s, lower dust. Fine fraction will have higher AC and more dust. All right, so now for your quiz for today. You already ready for a quiz? Okay, how much wrap's in this mixture? Correct.
Wow.
Yeah. Does it look like if any of you have seen asphalt mixtures fresh before, does it look any different from any other asphalt mixture? I don't think so. It actually looks kind of fairly rich to me. There's really been a long history of 100% wrap mixes. I think this is where the future is going to. Some of them are cold mix. Dr. Lee has done a lot of work on this. Hot in place recycling has been done. There's portable patching units, and then scalable plants. On the top, we have a cold in place recycler. That's somewhat along the work that Professor Bradshaw presented on. The bottom left is a hot in place unit where you basically use infrared heat to heat the pavement, scarify it, mix in some rejuvenator, and immediately place it back down. And then the bottom right is it's a Bagella patching unit, which can heat up small amounts of mix to make like utility trench cuts or pothole patching, small amounts of 100% asphalt. But for a number of years now, there's actually been plants capable of producing hot mix at 100% recycled. Oops. The bottom left hand is the cycling unit, which was run by the city of Los Angeles for a number of years, actually uses microwave technology to heat the asphalt. FHWA sponsored demonstration project 39 back in the 1970s, and they had, at that point in the 70s, some 30 projects that had RAP contents ranging from 69 to 100%. So we did it early on when we started recycling during the oil embargo, and then we kind of settled down to lower percentages. Super Pave came along, we went to even lower percentages, and now we're building back up. But these mixes have been tracked, and they actually have had good long-term performance. If you're going to do 100% RAP, when you size the material, when you fractionate it, you need to take a look at what mix you're going to try and make in the end, and you want to match those sizes. You know, if you're going to use all 100% recycle, that's your only aggregate. So your recycle needs to match the final gradation of what your specifications are. So this is an example from the plant in New York City. They have three, typical aggregate size mixes they use there: a sand mix, a top course, and a binder course. So they actually size their RAP to those fractions at 1/4, 5/8, and 1 inch. And we can do blends of those. You know, we blend the sand fraction and the top fraction to get the surface mix. We actually blend all three fractions to get the binder mix. We need to add recycling agents to these. We're trying not to add additional virgin binder, although you can add recycling agents to virgin binder to make softer virgin binders. This is just giving some examples of the dosage that to add, say you get 100% RAP mixture, we'd add 1% rejuvenator or recycling agent to get a PG 64 minus 22. We might need a little more of that to get a 64 minus 28, as this chart would show. You're really changing a couple parameters at once. You have a high temperature parameter for the binder, a low temperature parameter, and an intermediate temperature parameter. And the amount of recycling agent or rejuvenator that you add to get one of them to meet the specification may not be the same for all of them. Typically, we add at least the minimum to get the low temperature property to pass. If the mix is stiffer on the high temperature side, that's generally considered to be a good thing. Here's just some performance data on the 100% RAP mixture. We have a point down, there we go. Oops, sorry. Point down here, very low rutting with 100% RAP mixture. This particular, some of our highest rutting here is actually 100%. We had too much rejuvenator at this at 1.8 gallons per ton. So that was a learning process in balancing that cracking resistance with rutting. The typical mix used in New York City is 40%, and that falls way down here, very rut resistant, that bottom right circle. Similar to the overlay test, we've done this on the 100% recycled mixture, and that row of dots across the top there at the 100% line are all done on cores. So plant mix, field compacted, 100% or 100% recycled mixture, very long lives. Some of the outer ones we actually stopped the test because it had run so long, so they weren't true failures. So we're able to get very good cracking and good rutting performance with these mixtures. Low temperature cracking, you can turn around here. New York City DOT's standard 40% RAP mixture gives you a minus 21 grade on the test on the mixture. Just failed the minus 22 criteria. The 100% RAP mixture we tested gave minus 29, which would exceed the minus 28 we'd like to have in Rhode Island. So we can make these mixtures, if we engineer them properly, to have good rutting properties, good intermediate cracking temperature properties, and good low temperature cracking properties. That's just a quick picture of the plant. It does take some specialized plants to make it. Field performance of the mixture. Mix placed in 2007 and again in 2012. And actually we see less raveling, less loss of surface sand in the 100% RAP material compared to the New York City standard 20% or the vendor's 20% RAP material. Looking at savings, how much can we generate? What's it worth for the agency? And it's really a combination of things. As there's a cost for aggregate and binder if we have no RAP. There's no cost for aggregate binder if we're using 100% wrap, but then there's a cost for rejuvenator, there's a cost for plant controls to make sure there aren't emissions. More testing, more processing of the wrap have cost, but there's a potential for significant savings by using 100% wrap. Not only in monetary savings to stretch our infrastructure budgets, but also in natural resources. It does pay to keep your wrap dry. Now to sum up, there's really good data out there, both field performance and laboratory performance to support the high wrap and RAS mixtures. Is it all mixtures? No. I mean, we have unfortunately seen cases where people have just added the wrap and RAS to the mixture, not done any changes, not done any engineering, and we've not had good performance. Softer binder grades or rejuvenators are often looked at. They certainly can help compaction. That can be a problem, cold weather temperature work, and they can help low temperature cracking based. From what we've seen, the rejuvenators seem to be more effective than using softer binder grades. Some of the rejuvenators now are even themselves byproducts of recycled materials. We're looking at rejuvenators that come out of sewage plants. We're looking at rejuvenators that come out of paper processing. Dust does have a big impact on getting the volumetric properties of the mixture to right. You need good stockpile, good management practices in separating and processing the recycled asphalt pavement. Need to account for how much of that aged binder really is effective in the mixture. Intermediate cracking is really the hard part, and I think that's where agencies need to be especially aware, as well as commercial interests. Most commercial pavements are relatively thin, that we have a stiffness of the mixture that is appropriate for the pavement structure we're putting it on. Again, softer binder or rejuvenator can help, as can extra binder if we're counting that some of it isn't effective. But in the end, we always need to be aware of that permanent deformation, permanent strain potential, or rutting check. With that, that's kind of the end of my spiel on recycle. One of the other side things we do is racetracks, and this is actually paving the National Corvette Museum's racetrack in Bowling Green, Kentucky back in June. Any questions? Yep, too much technical data. Yes, sir.
So I was wondering your opinion about future recyclings of wrap. If wrap is used in a pavement, what do you think will happen the next time that pavement is reused and recycled again?
That's a really good question. There's a slide I was looking at last night and took out, but as the asphalt ages, like many things, it ages rapidly initially, and then it starts to taper off with time. So, you get that tapering off point, then we recycle it, we move it down, and it's going to go back up in that case. There's kind of a limiting stiffness, it seems like, that you get to with typical wrap type materials. So it looks like it can be recycled, again and again. It's not something that we've done where we've artificially aged. That's probably maybe something that research that could be done in the future, where we could rejuvenate mixtures, artificially age them for equivalent of 20 years, and then rejuvenate them and retest them and see if you can get the same properties. Some of the similar concerns that have been is that some types of rejuvenators you have to be careful with because they will themselves prematurely age. That's been a concern that we've looked at. So when we do cracking tests, we actually do a long-term aging protocol, long-term being only 5 days at an elevated temperature, but it's to simulate a period of like 6 to 8 years. So we're not testing the fresh material, we're trying to look at what it'll be like a number of years down the road. Yes, sir.
Is the rutting problem associated with more accidents that occur with vehicles versus the cracking side? Obviously, I would imagine a lot of accidents due to cracking, but I see numerous intersections where the rutting can be a serious problem, and I'm wondering if there's a correlation between the number of accidents that may occur.
Sure, you're exactly right. When I worked for Virginia DOT, rutting was foremost on our minds. And part of that's really twofold. Rutting often happens 2 to 3 years after construction. So if you get a a pavement failure in terms of rutting 2 to 3 years, the general public's gonna notice that, right? Like, you just repaved this road and now it's failing and we're repaving again, so they're unhappy. And a secondary part of that is that if you have ruts, they'll trap water, and so hydroplaning, where the tire is separated from the pavement by water, is a very real concern. Most states will limit maximum rut depths to 1/2 inch to prevent hydroplaning. So definitely, rutting is a safety concern. Cracking is not typically a safety concern, but it is a performance concern. And so if you're gonna balance that, you probably don't truly balance it to the best cracking performance side, but you balance it to a safe rutting criteria and then get the cracking as good as you can get. And that, again, why I emphasize, I didn't spend a lot of time on the rutting tests. In most cases, RAP improves the rutting resistance, but as we add additional fluids to counteract the effect of asphalt, as we add rejuvenators, it's certainly possible to go too far and create a rutting potential. We need to be aware of that.
Is there any problem with shoving between the top binder, the top course, and
Typically, I would consider shoving and rutting to be the same type of phenomenon, instability of the mix. Bond plays a role in that as well if you don't have proper bond between the layers. Historically, if we use proper tack, it shouldn't matter whether it's 100% recycled mix or a virgin mix to get a good bond to stop from a shoving standpoint. Well, any other questions? Well, again, thank you very much for the opportunity to speak with you this morning.
Please, Brian, could you come up again? You know what we had here is we prepared one gift for you, I believe. But this is not the one your size. So let me quickly check. I got the right one, or I think I have the wrong one. And it looks like this is the right one. I know the old one is not that cold, but sometime when you go outside the field, you may need this one. So we like to present URI shirts.
Oh, thank you very much.
Suitable. Okay, thank you.
Thank you.
Okay. Great. This is you can fit here, all right?
Thank you. I could have used that yesterday.
Yeah, that's right. You may come again to New Jersey and then New York City. That's that you may need, all right? Okay, with this, we are going to finish up the first segment of morning section. And then we'll have 10 minutes break. Then we'll come back, and then Professor Hunter will moderate the second section of this forum. Thank you. Okay, so you got to go, I believe.
Yes, sir.
Yeah, that's me, so, thank you.
Nice to meet you. Thank you so much for
You didn't coffee, anything?
No, I. Here's your power supply back.
Oh, yeah. Did you walk? Oh, okay, sure, that's true. All right, that's a good, he's nice.
With that shirt.
Oh.
Because I got it too late.
Yeah. I hope it's not that too big.
No, that should be great.
The larger size better.
All right, now, okay.
Thank you.
Good job, good job.
Thank you.
Thank you.
I want to make sure what size was my secretary or large. No, actually extra large is yours. Just I got a wrong one.
Okay.
Thank you
Large
so
one.
much.
Yep.
Yeah. Large is-
Very nice talk, Mike Greenfield, here at URI, Chemical Engineering, I'm actually speaking.
Oh, cool.
Very, very nice.
Sorry, I can't stay for your
Oh, no, that's okay.
presentation. I'm trying to get home
I'm sorry.
for
I'm glad I checked with you.
Oh, yeah.
Same one for okay.
children's last Halloween.
Oh, wow,
Yeah.
yeah.
The
Totally makes sense.
Mike has in.
Well, I do asphalt
Great,
at the
yeah.
molecular level.
Yeah.
And I can try to send you some summary papers
Yeah.
of what we're doing.
That'd be
So
great.
we can zoom in on the small length scales.
Yeah.
Right.
And look at the chemical changes and how that affects things.
Yeah.
I think with the rejuvenators, those are really important areas. We try to break up some of the asphalt agglomerations.
I think
to
it-
just solve it.
Yeah, that's I think you can go next item. Like you work on mostly virgin asphalt binder.
Right.
Now you need to add
chemical
those
effect, right?
regenerator and then
Right.
how we drag.
That
He has-
chemical effects
yeah.
always make me think about the asphalt
Yes,
shingles.
yeah.
That's such different chemistry.
Right.
And those are changed so much making the shingle that it's, while it came from asphalt, it's like the difference between dough going into the oven and burnt cookies.
Right, right.
Chop up the cookies and put them in, but then it'll be
Yeah.
burnt.
Okay, so I think it's great that you guys can get together because we are very happy to have him. He's a chemical engineer,
Right.
but he's working on the modeling of the asphalt binder, and it's fantastic work. Someday you guys can exchange the technical paper, the article.
Do you want me to put my things on your computer, by the way? Is that
Yeah.
like, okay.
Go ahead. Okay.
Very good.
Very nice to
Yeah.
meet you.
Nice to meet you.
Yeah.
Have a safe trip
Yeah.
back.
I know.
Enjoy. I hope you make it back in time for the.
Yeah.
Yeah.
It would be nice if you can hear from him, but well, you cannot. Okay, that's right. I could take some of that.
I was gonna get some for the road.
Michael, how are you?
Good, how are you, Chris?
Excellent. So,
I am
what I was
copying-
telling.
What was it?
Well, I was telling me.
Well, maybe you can do that. First of all, they're beautiful. Yeah, Miami. I saw the Miami. Crystal, Rhode Island. All right.
Do you want to put it on the computer now?
Oh, yeah, sure, if you'd like to. Go ahead and get that out.
Can I go and then get in? I tell him everything. Okay. Okay. Second section will start, so you can take the copy. It's okay. Yeah, you can go out. Okay.
How are you?
Good.
Yeah, good.
Okay, let's get in.
Yes.
Yeah.
Happy Halloween.
All
I think it's right there
You
with
can
you.
get it.
Oh, no, it's not, that's right, that's DVD, okay.
No, it's
He will have to wait for the
Hi,
computer.
yeah. Become so impatient.
You can get in. Yeah. You can log in. Okay. Yeah.
It doesn't seem right for us to wait for it.
Right.
You can log inside. Okay. All right. All right. You can get in. Hello. Welcome. Hi. Yeah. Yeah. You can get in. Hello yourself. Hello. My wife. Great to meet the table. Thank you.
So to conclude,
Let's get in.
let's give 3 15-minute talks, each run 10. That fixes the 15. That doesn't.
It might be. Okay.
Yeah.
So,
That's fine.
we're gonna.
Okay, I think whenever you are ready.
Yep, we're ready.
let's start with it.
Well, good morning. Getting ready to start the next session. We're going to have 3 presenters for us. Professor Michael Greenfield from Chemical Engineering, then Professor May Gindy from Civil, and then Professor Natasha Thomas. And at this point, we're going to bring forth Professor Michael Greenfield with a presentation on molecular and mechanical modeling of asphalt rheology and chemomechanics. Professor Greenfield.
Thank you. Good morning, everyone. Welcome. We're going to try to accelerate our presentation so we can get to lunch on time and have time for lunch before we come back for the afternoon. So if there's pieces that seem chopped, that'll be why. I'll jump over some slides. Feel free to ask questions at any time because I want to make sure that that your questions get answered. So I'm going to be telling you about some work we've been doing for a number of years now. If you're a regular at the forum, you will have heard some of this before. We've heard a bit of this already about what makes a good pavement. Eventually, we would like a pavement to be smooth and durable And the kinds of questions that we want to try to answer is, what do these mean in terms of the influence of the asphalt chemistry? You may have hated having chemistry. We'll try to make it fun for the next 10 minutes as we look at some of the questions about asphalt chemistry and what happens on very small length scales about how the asphalt chemistry impacts the pavement. And so to get started with this, I'd like to show some pictures of failure modes. The picture on the left is a rutting picture that you may have seen in some large number of rutting pictures. This is a picture taken, I think if we zoom in on the car, it's from the 1950s. And so this is rutting that happened a long time ago. This picture on the right, this is up in Boston. I took this a couple years ago at a conference. This thing over here is the Boston I'm horrible with the mouse. We'll just, the thing in the upper right is the Conference and Exposition Center. And
do you need the pointer?
If you have a laser pointer, I'll take
Yeah.
that. Sure, that'll be more effective
Yeah.
than this.
This is the way. Press those button.
Yeah.
All right.
So up there. And what you can see to some extent is these grooves in the pavement. This is where the Silver Line bus comes out and then sits and waits. And so this pavement very recently is showing very, very visible signs of rutting that are somewhat difficult to get with the camera. We're familiar with a bit of cracking. This is Plains Road. If you came in from Route 138 through by the train station, you drove over these cracks. And so this is some examples very close by. So what does it mean? What is the connection to asphalt chemistry? There was a mention in the previous talk about superpave that leads to these specifications about high temperature conditions and low temperature conditions under which the pavement is expected to perform well. This is a chart from some lab work that was done elsewhere on a big machine called the Accelerated Loading Facility. The important part here is that certain pavements that were expected to be performing similarly at certain high temperatures actually had very different amounts of rutting that occurred. And so the specification itself is not enough to guarantee that it's going to be showing the same performance. Instead, there's connections to where the asphalt is coming from and what is fundamentally in the asphalt that's leading to those properties. And that's what we're trying to connect up to. So the way we think about asphalt is over many different length scales. Here's the cracking picture again. If we look at a little picture of a little piece of that road rather than, say, a 10-meter stretch, that within that smaller centimeter scale, we can imagine there's the different rocks and the different asphalt binder. This is a picture taken from work from Marty Sad in mechanical engineering here at URI. If we grab a little teeny piece of this and zoom in, then we can be looking now more on the micron kinds of scales at what's within asphalt. These are two pictures from the literature, different methods, looking at how the asphalt, within just the asphalt binder, between the rocks, what kinds of microstructures form. What we're doing in our calculations is if we look at a little teeny piece within one of these micron scale pictures and zoom in yet more over to nanometer scales, how are the molecules packing together and how does that impact the properties? So zoom, zoom, zoom again, with each of these being maybe 1,000 times smaller, and we get to where we're looking on the calculation. So we're looking at very, very small length scales. Why we want to be looking at this on the molecular level is looking at how the specific molecules contribute to the chemistry and how these different sources of different asphalts connects to the mechanical properties through what the molecules are doing. And so in short, what we do, back in physics class, you may have learned that force equals mass times acceleration. That's what we do. Where molecules are tells us the forces, which accelerates them, changing their velocities, changing their positions, and we go around as many times as we can get big computers to do. So this depends on the size of the computer and the patience of the graduate students running it. So just a quick warning, some organic chemistry very briefly. This is the kinds of systems that we simulate. This is our model on the computer of different asphalts. It has different molecules that represent groups called asphaltenes, polar aromatics, naphthene aromatics, and saturates. And so an important part for us is that we've got a bunch of different compounds and that each of them is chosen to have some sort of resemblance to real molecules that have been found in various kinds of studies of geochemistry, organic chemistry, asphalt chemistry, and such. So we choose these, we put models of them into the computer. We don't have to buy the individual compounds. I would not advise making an asphalt by trying to buy the individual compounds. Only do that if you look at your asphalt and say, I wish I could make it 1,000 or 10,000 times more expensive. Then you try to build it up bulk compound by compound. This is just something we do on the computer instead, because on the computer it's a cheaper simplification. So what does it mean for us to be simulating asphalt? So here we have one of these boxes that is nanometers on an edge. We can think of this as being part of a continuum. If something comes out the right side, it comes in the left side. And this is a box that's simulated to be about 140 Fahrenheit. When there's a mouse, okay? So as we run a simulation, what happens is this thing is moving back and forth. The different colors here correspond to some of the heteroatoms in asphalt, nitrogen, sulfur, oxygen, and pretty much you can see things are just shaking around a little bit. Everything that I'm going to be talking about is looking at when this thing is shaking around, how does the way that it's shaking around tell us about the mechanical properties? If it's warmer, it shakes around a little bit differently. This is same kinds of compounds, slightly different arrangement of the molecules. There's a mouse on the screen somewhere. And yet, well, if I just click, does that, no? I'm very mouse impaired. Here we go. So higher temperature, if you watch the colored ones, you see they're moving around quite a bit more. There's more motion at a high temperature. This is kind of chemistry at work. Higher temperature, things move more quickly. And from that bigger amounts of motion, we want to infer more about the mechanical properties. What we specifically look at is what individual molecules are doing. If we take this and make most of it invisible, it's a computer, we can do that. We can see just what some individual molecules are doing, and we can zoom in and look at what those individual molecules do. And here's just one picture of that, assuming I can find the mouse. This is at a higher temperature still, and you can see that these are particular asphaltene molecules. Over time, they point in different directions. They're kind of moving around. They look sort of like flying birds. All around them is the rest of the asphalt is just kind of hidden to make us be able to see these. And what we're interested in is how these move around, and we're interested in that because the extent that they move around tells us about the asphalt. Some analogies to this would be that if you imagine jogging on a sidewalk, that's much easier than jogging in a swimming pool, or doing a forward roll in the grass, doing a forward roll in a pool. Those are very different experiences for us because of the fluid, the water versus the air. And in the same way, the way these molecules move in the asphalt tells us about the mechanical properties of the asphalt. And yeah, so that's what we do. So what does this mean? It means we then throw it into a bunch of computations, and we get something that goes from no change in direction down to lots of changes in direction and pointing someplace else. And if it's hot, that happens quickly. As the system cools down, we're moving in this direction, and things cool down much more slowly. These time scales here are very, very, very small. This is 1 nanosecond, 2, 3, 4 nanoseconds. We essentially fit these and then extrapolate them all the way to 0. Here, this is a log scale, so 0 is infinitely far down. These are getting pretty low right away. These, it takes much, much longer. So we extrapolate, and depending on the direction of the screen, this extrapolation could easily reach Providence or Boston or New Hampshire, depending on which temperature we're looking at in terms of how big the extrapolation is compared to the size of the scale. So it's a huge extrapolation that we make to get to the overall amount of time that it takes to relax. That gives us how long things take as a function of how cold it gets. And we can compare it with experiment under certain conditions, and we're the correct order of magnitude. In terms of the viscosity of the asphalt, this lets us predict the blue line with the dots. The greens here are various experimental data on different asphalts, and so we see a similar dependence, so we're very happy about that. So this is one of the mechanical results. There's various equations about how we do this. In the interest of time, fortunately for you, we skip over them. And what this leads to is complex modulus is a way that asphalt gets specified. We're looking here at what's called the phase angle as a function of the complex modulus with a few correction factors to adjust for the different temperatures. And our results are these different colors here, these messy curves, these are different temperatures. And this line here is just very roughly showing a tendency of them overlapping under various conditions. This is more of the region of interest, and then further way down here where we can't calculate because it takes too long. And this is a side effect that we're still working on. These purplish lines here, these are results from something called the CAM model. This is a traditional model of asphalt rheology. And so these are curves that come from various asphalts that have been published. And what we see is what we're getting from our simulation is a similar kind of dependence. I mean, we can argue about how these look a little bit different. but in fact, various asphalts all look different. This is those same two curves. This is a bunch of different asphalts that get used in Minnesota in a publication that happened to publish lots of nice details. And so you can see that asphalts typically have curvatures like this, and our simulation result is looking like that also. So this is really exciting for us because this plot, which we just published last month, is the first time that there's a direct comparison from the molecular level with predicting one of these curves with the experimental values. So with it, we can do a lot more analysis, but in the interest of time and letting you hear the other presenters and also eat, let me jump to the conclusions. The key for us is that to connect the nanoscale of the asphalt to the macroscopic properties, the importance for us is looking at what the chemistry is of the molecules, tracking those in detailed calculations, and following how that influences the mechanical properties. Along the side, there's lots of small details that we've got to do right that are interesting in their own right, but perhaps they're much too long a story to tell in the time available. So some of the upcoming things we're looking at, oxidation, such as in the previous talk with recycled pavements. That's something we're interested in now. How does the properties change when we oxidize the molecules and look at the aged asphalt? You're looking even more at how composition changes in environment, new additives, new ways that people modify asphalt that there may or may not be support for doing in terms of the politics. How do we expect that to affect the science of the asphalt? So I'd like to thank you for your attention. Happy to answer questions. I'd like to point out these are the graduate students who contributed tremendously to the work that was done. If it was not for the efforts of Lichin and Derek and Mohammed, I wouldn't have been able to tell you about the work here today. So thank you. Happy to answer any questions.
Well, I would just ask a question too. One is about compaction.
Right.
I haven't heard anybody really talk about compaction when they're laying the asphalt down. And the other was, what would you say in conclusion of what you presented?
Both excellent questions. In terms of compaction, the length scale of compaction is much, much larger. I'm going to try to jump towards the beginning again and say that on these kinds of scales, the voids that will be present making up the VMA, those voids would look really, really big compared to these scales. So a void, on this scale, imagine a void being the size of the entire wall, perhaps, or even bigger than that. So compaction is much bigger than what we're looking at, so I can't really say a lot about it, I would say. Very important for the real performance. Wrong approach for us our approach would be the wrong approach to be trying to answer questions about it. Overall conclusion, I would say that the source of the crude oil is an additional variable that is potentially going to be important to be looking at for the performance of the road. Again, there's some large-scale studies that are looking at if we pave a long stretch of road and we pave 1 mile with a crude oil, say it's a 68 minus 22 from one source, say from Venezuela, and then we use another one that's coming from Canada, then another one that's coming from the Middle East. How well do each of these consecutive sections age when they're the same PG grade, the same company doing the manufacturing, same outdoor conditions, same traffic because the road's in the middle of nowhere? How do these different roads behave? So these are some ongoing experiments in various hot, cold, wet, dry places that will be giving some good experimental evidence about how important it is to consider this crude oil source. It looks to us like the molecules do something that makes it important. Those experiments are really going to show how it translates through the entire road building process.
One other question?
Great.
Thank you again.
Thank you.
Next we have Professor Gindi, one of our great structures faculty from civil engineering. And her talk will be looking at ground penetration radar.
I have no warning signs on this one. All right, good morning. My name is URI Gindi, and I'm a structures professor here in civil engineering. And I'm going to talk a little bit about a new project. So I don't have a lot of results to show, but this is one that we're looking at for ground penetrating radar and looking at the inspection of concrete bridge decks. So what I hope to accomplish today is to give you a little bit background of what GPR is. So what is GPR? How does it work? How is it helpful? And how are we using it in Rhode Island?
I can see how popular Professor Gilby.
I think class just let out. I'm drawing them. Actually, a lot of these students helped me with this project, so maybe I'll have them come down. All right, so what is ground penetrating radar? Ground penetrating radar is a high-frequency electromagnetic wave reflection that is basically emitted into a subsurface, and it's looking to get the reflections back. And how long it takes to go through a medium and come back, that two-way travel time will tell you something about that medium. Will tell you the location, the depth. And so what is the ground? The ground can be anything. It can be soil. A lot of geophysicists use this. It could be rocks. We use it on concrete. And it has a wide range of applications. You can locate buried utilities, so anything pipes, mine site evaluation, forensic investigation, archaeological digs. These were all the early applications to it. And then for our purpose, we are looking to locate reinforcing rebars in bridge decks, determine where their location is from the surface, so the concrete cover, how much protection they have, and also hopefully to define general areas of deterioration. So we're looking at corrosion of rebars, voids in the concrete, so that sort of application. So that is our ultimate goal. All right, so how does GPR work? It's basically an echo. So if you imagine yelling down in a well and waiting for that reflection to come to you, that two-way travel time, the time that it takes a signal to go down, hit an object, reflect back up, that will, that's basically how GPR works. A lot of fish finders, they use that to fish. So here's the boat, it's got a fish finder. It's continuously sending a signal as it traverses longitudinally here across the water. And once it hits an object, okay, it will have a little ping, okay, that amplitude will have a reflection. So that's the location of fish, and then you can also see that it maps any other obstructions that it gets its way. So that's the bottom. So two-way travel time and also the amplitude of that signal will tell us something about the medium. So it emits a radio frequency signal. It detects these echoes that are sent back, and then we build images off of it. So this is a line scan here. This is an antenna. This is an air-coupled antenna, which means that it doesn't touch the surface. So it goes through air. It hits the surface. That's one reflection. That's the first reflection, and you see a peak here. Then part of that reflection frequency will go through the concrete, hit another medium, which is rebar, reflect back, and then a portion of it will transmit through to the bottom and get that. So we're looking for these peaks to tell us something about the medium in terms of amplitude and also of their location. What frequencies do we work with? So if you're looking at the electromagnetic spectrum, we are in the we're about at 1 gigahertz. So we can go from 3 megahertz to 2 gigahertz. So we're in this area here in the microwave frequency range. For our application, we are using a 1.6 gigahertz antenna. It's got a bandwidth, so this is the bands of the frequency that it operates, and most of the signals, the central frequency is a 1.6 gigahertz. The largest interference, interference here is anything that is also operating in the same frequency spectrum that will mess with our signal, and most of it is basically cell phones, two-way radios, things that operate within the same frequency range. In terms of power, our GPR equipment emits very little power, about 1% of a cell phone, so it's fairly safe. So that's not a problem. In terms of penetration depth, so how far down can you see is a pretty important one. And radio waves are just like any other waves. If they hit interference or if they hit an obstruction, so if you're listening to your radio and you're driving through a tunnel, you tend to lose your signal. So it doesn't have that direct contact. Same thing with a GPR. Penetration depth and frequency are related, but also it's important to look at resolution. Okay, so here you have an antenna. This is T's for the transmitter. That's the one that sends the signal out. R is the receiver, so it will receive all the signals that bounce back. And you have here two objects, let's say rebars that are on top of each other. So depth is important, yes, but also resolution. So how well can it distinguish between two objects that are closely spaced together? This is a general description between, shows the frequency of antenna, so 200 megahertz to a 2 gigahertz, and also the penetration depth. Generally, if it's low frequency, it can penetrate deeper. So you use this for if you're looking at soils, buried objects, utility, things like that, you would use a low frequency antenna. And then if you're going on the high end, you're basically looking at shallow. So you're getting a higher resolution, so you can distinguish more clearly, but you're only limiting yourself to a shallow. So this is about a 6-inch. We're somewhere in the middle. We're about an 18-inch depth. So this is our antenna here. It's a 1.6 gigahertz, and we're looking at 1.5 feet, so an 18-inch. Typical concrete bridge decks are about 9 to 10 inches for the deck, and then you have anything from a 3 to 5 inch overlay if it's been overlaid several times. So we bought our antennas just to suit our applications. Okay, so what is it a typical scan would look like? I'll show you the equipment later on, but a typical scan is basically you're reading the horizontal distance here. The horizontal scale is distance, so this is as you're scanning a bridge deck. If you're taking a profile, as you're walking, it's continuously sending these signals down into your surface, and it's looking for these reflections. Your vertical scale here is the two-way time, okay, or you can convert that to depth. Okay, so in this picture I have here, feet is the horizontal scale and inches in depth. And this is the reflection that we're looking for. These reflections are rebars, so they're evenly spaced here. And then the peak here, and I'll tell you a little bit about why it looks like a parabola, but this is the top of the rebar. And then you have some noise in the bottom, or things that just don't reflect. If you take a slice of one of these, this is the 2D image that we're talking about. So they're continuously taking these scans. This is a line scan, and they're basically putting them next to each other, and they're building this 2D image. So this is the first peak here is called direct coupling. This is when the signal just goes from that transmitter to the receiver right away. So it's a false signal. So that's basically your zero line. That's your surface. And then you're looking for any of these peaks here. All right, so why does it look like a hyperbola? It's because as you have your antenna on the ground, which what we do on a concrete bridge deck, is that it sends out your signal as a cone shape. Okay, so it sends out your antenna, your signal as cone. So anything that reflects within that cone is going to come back to the receiver and say, I've located something. And so if your antenna is here, and this is your object that you're looking for, the first signal that comes out is going to follow that cone. It pings it at this location, comes back to it. So it thinks that it's taking so long, because it's a diagonal time, right? So it's taking it thinks that it's lower than it actually is. The antenna keeps moving, and it's sending this cone-shaped signal out until it's right on top of it, and that would be the shortest time, because we're measuring time, two-way travel time. That would be the shortest time that it sends its signal, comes back to it, so you're right on top of it, it passes it, and then again, it thinks it's slower than it is. So you build up this cone shape, and so you have to, in your post-processing, you have to collapse that hyperbola into a point, which is basically the peak here. So it's called migration. Okay, so how can GPR be useful to us? Really, we're using it in Rhode Island in two ways for condition analysis of pavement structures. So this is an air horn, they call it an air horn antenna. It's hung in the air, and DOT already has a vehicle. You may have seen them. They've just completed their system-wide scan of their pavement of some roads that they have. And they basically have this radar. It's about 18 inches off of the surface, and they travel down at highway speeds and lanes, and they're looking at pavement layers. They're looking at different thicknesses. They're looking at condition of pavement. So this is called an air-coupled, air-launched horn antenna. This is all the same name, for different names for the same thing. So there's no contact, highway speeds, automatic velocity calculation, looking for thin layers. The bad thing is that you can't tell everyone to turn off their cell phones, so if you're driving around and people are on their cell phones, which there are, you get some interference, two-way radios from truck drivers, things like that, can mess your signal. So the application here is evaluation of pavement layer thicknesses, looking at anomalies in the pavement, detection of cavities, sinkholes, anything that's faulty with the pavement. So I took this from New Jersey. They were doing this, I think this is in 2008. So what can you do with this? So you have all this data. How do you integrate it? So data integration is one. So we have all of this data. We have cores, we have pavement evaluation, we have pictures, we have, how do you put it all together? And so this is one system where you can have a video or some photograph of where you're located, so GPS, anything like that. You have your map here, and basically as you run this video, it's going to show you the condition of your pavement. So this is all the layers. This is the bottom of the pavement, bottom of the base. This is any data that you've collected, cores that you've collected, images that you can have. So this is a warehouse of all of this data coming together for a network level type management. Is that 10 minutes? Okay. So how is it helpful to us? This is for bridge decks. This is what we are trying to do. This is our equipment here. I'm going to run through it a little bit quickly. This is ground coupled because it's touching the ground. We're able to resolve thin layers, but we have to go much slower. So it's at a very slow walking pace. And this is the type of maps that we are aiming to provide Rhode, is basically deterioration. So the hot zones here are where we suspect there to be delamination, corrosion, anything of concrete deck deterioration. And if we do this on a network level, we can say, all right, on this particular bridge, 20% of your deck in this particular location. So maybe they go in, is deteriorated, so they go in and they rehab that specific area. System components, you got a controller, you got your antenna at the bottom, and a DMI is a distance measuring instrument that tells you where you are along. And I'll just show you a few pictures of, we've tested 2 bridges, one right back here by URI, the Yagu Mill Pond Road. It was a 4-span continuous steel girder bridge. The concrete deck looked pretty good. It had a latex modified concrete, so it's a rigid pavement, has no asphalt on top of it. So we test, it's a 460-foot length bridge. And we tested half the bridge, and we would go on a 2-foot grid. So we'd lay out a 2-foot grid, and we'd do longitudinal zigzag back until we scan it. And we'd also have to do the transverse. So these are just some pictures of us laying out the grid, traffic control, and then here's our equipment, longitudinal, and then also transverse. Just this past Wednesday, we also tested the Mill Gut Bridge in Cold State Park. This one was a simple span pre-stressed concrete bridge. The top of the deck looked pretty good, but this bridge, if you're looking at the bottom, it's posted, it's in somewhat bad condition, so it rates lower. And again, this is just some of our pictures from our test. All right. So this is the type of, I should mention our sponsors. So DOT sponsored a project with URITC. And so this is just some of the ongoing work. We just started this work. We're slated to test about 10 bridges throughout. And so we'll probably slow down when the condition, when it gets rainy or snowy, can't test out in that condition, and pick back up when it's good temperature. Don't forget to vote yes on. Okay. All right, any questions?
Any questions for Professor Getty? Perfectly.
Oh, my hat's on.
Well, that's where, if no one else, so if a cell phone is so much more powerful a signal, why not use a more powerful signal and get better signal to noise ratio?
Say that again?
You said that cell phones have much more power than this is. Why not choose a more powerful radar to get better signal to noise?
We actually do pretty well with, it's basically on frequency. So the 1.6 gigahertz, we're looking at the top layer. The power thing is in terms of safety. You know, it's easy, you know, it's not gonna be harmful for you to stand next to the GPR. Yep.
That was my question. The operator of that equipment are they exposed to any kind of danger from the radar?
No, it's safer than using your cell phone. It's fairly safe. Because all the students that were doing it are right here. It's very safe.
Yes, it also.
You're glowing. Very good, thank you.
Give another hand for Professor Gendy. Actually, is Professor Thomas around?
You went to lunch?
She went to lunch already, maybe. Well, then maybe we get to go to lunch earlier. He shows something next in terms of exhibition and poster session. Do you want to describe what's going on there?
Okay.
And thank you for attending the session.
Thank you for Professor Hunter. That was probably miscommunication. She thought she may do afternoon presentation, but she's supposed to moderate the afternoon. But she'll be here. Okay? So, yes, as Professor Hunter indicated, we have wonderful exhibition along the corridor. So the bad news is probably we cannot hear from Professor Thomas, but good news is you have more time to interact with our practitioner, consulting firm and then agency. And also second floor there are some posters as well. So why don't you have some interaction with the exhibitor and come to the US Club by 11:45. How about that? Okay, thank you, ladies and gentlemen. That's interesting. he was, with the oh, really? He was interested in the good-looking gentleman, so he wanted to take pictures.